Welcome to Heart of Mathematics. This is Fractal Dimensions, the first in 2 videos. So let's first get some idea of dimensions. So when we define dimensions, let's talk about how we're talking about in which or how many directions you have to go to replicate an object. The second definition we'll use today is scale factor. So when we're replicating an object, we want to know the scale of the pieces in the new object. So for example, if the new object has pieces half the size, our scale factor is 1/2, which is equal to 2, and we'll see that in a moment. And the third definition we'll need today is the number of copies. So how many copies of the original object are necessary for the new object? And the relationship shown here at the bottom is we take the scale factor, raise it to the dimension, and this gives us the number of the copies. And we can rearrange this to solve for the dimension, where the dimension is given by the natural log of the number of copies divided by the natural log of the scale factor. So if we know the number of copies and we know the scale factor, we can find the dimension of the object. So let's do some simple examples here. Let's look at a line, a square, and a cube. So intuitively, we know what the dimensions of these shapes are. So let's suppose that a line has width 1. So if we're replicating this line, we take this line, and to replicate it, to make it look like itself, we need 2 copies of the line, each with width 1. So our number of copies here, we have n is equal to 2. Our scale factor is equal to 2. And our dimension here is the natural log of 2 divided by the natural log of 2 equals 1. And it makes sense because we think of 1 as a line as a one-dimensional object. If we think about this with our scale factor, if we think about each of these lines rather as width 1, we think of it as width 1/2 to cover the same amount of ground. If this entire interval still had length 1, each of these line segments has to be half of a unit long in order to cover the same distance of one segment. And that's how we get our scale factor of 1/2. Remember, we invert it to get our scale factor of 1/2. So let's look at our square. So we take our square, and if we were to replicate it to make a bigger square, or to keep the square the same size, so if this is 1 unit, and this is 1 unit, we need 2 copies of the square along each side. That's not a very good square here. So we need 2 copies of square on each side. So we need a total of n equals 4 copies of the square, where the new side length of the square is 1/2. So our scale factor is equal to 2. Again, we scaled down our squares by a factor of 2, and we used 4 of them to build our new dimension. So now we take natural log of 4 divided by natural log of 2, and we see we get 2. So a square is a 2-dimensional shape, and this makes sense with our intuition. Now a cube, we do the same thing. To build a bigger cube, first draw out our bigger cube here, we need 8 smaller cubes, where each of these smaller cubes kind of builds our block together. So each of our smaller cubes has side length 1/2 of the original builder block. So here I've outlined one of the cubes. So my n, if I think about it as I have 4 cubes on top and 4 cubes on the bottom, I need 8 total blocks. My scale factor again is 2. So my dimension is natural log of 8 divided by natural log of 2, which equals 3. So my cube is a 3-dimensional object, and this makes sense. Again, with our intuition. So when we're talking about different shapes right now, squares, lines, cubes, let's talk about a triangle. So let's suppose that we have this shape here where we have a triangle. We've replicated our triangle here, and I've outlined it in red. On the inside of our triangle, it takes 1, 2, 3, 4, 5 copies of the inside triangle. And when we're scaling this down, when we look at this, we say, well, how big of a scale did we have to take the original triangle to build this new triangle? So if we think about it scaling down or scaling up, we can use our scale factor. So here, if we look at the size of the side length here, we had a side length of 2 for our base on our original triangle. For the new side length, we had a base of 2 times square root 5. So by symmetry with our triangles, if we look at the angles, if every side on our small triangle is multiplied by square root 5, we get our big triangle. So our scale factor here, thinking about scale factors is a different way, we get square root 5. If we scale up, instead of looking at shrinking our triangles, we scale up, we can see a different way of defining our scale factor. So to find our dimension, let's look at the formula S equals D to the 5. Or excuse me, D to the N. So we know our scale factor, square root 5, and we know our dimension is D, and we know our N is 5. I'm going to just put a little 1 power there. Square root 5 we can rewrite as 5 to the 1/2 power to the D equals 5 to the 1. Using exponent rules, we can write this as 5D to the 1/2 equals 5 to the 1. The bases are the same. This means our exponent's the same. So D over 1/2, or excuse me, D over 2 is equal to 1. So this means our shape has to have 2 dimensions. So our triangle is a 2-dimensional shape. And this makes sense. So let's look at another object here. This is what we call the Koch stool. So if we have a starting length of 1, where we take a segment and we break it up into thirds, and at the first third, we kind of pop it up where we have a 1/3 rise in each piece. So we have 5 kind of line segments that build up this kind of stool position. And at the next step, every time we have a line segment, we put in one of these pieces. And this is how we form this sort of shape. And this is one segment. The next segment, every little line segment, we would take that little line segment and we'd pop out the middle section and form a new stool. So here, when we're looking at this, for the new shape, it takes 5 pieces to build the new shape. We've got the first shape as we build along here, and the second shape in blue here, and then the third shape in red here, and the second shape, or the fourth shape in blue here, and the fifth shape again in red here. So it took 5 of the original segments, sorry, fifth shape in red here, 5 of the original segments to build the new piece of the puzzle. So our N is equal to 5. And our scale factor, our scale factor was a size of 3 because it was unit length 1, and we shrunk it down to be size 1/3. So our scale factor is 1 over 1/3, or 3. We could also think of it as it was unit length 1 and it took 3, and now it's 3 times as big if we were to stretch it out. So now when we look at our dimensions, we're looking at 3 to the D equals 5, or otherwise D equals natural log of 5 divided by natural log of 3, which is approximately 1.46. So this shape doesn't live in a 1-dimensional land. It's not a line, and it's not a 2-dimensional shape. It's not quite a square. So this is kind of an in-between dimension. This is what we start to look at as fractal dimensions. So let's look at another example, at the Menger sponge. So this is an object that starts out as a cube, and then we start taking away shapes. We take out the middle cube on each side, and we take out the middle cubes on each side, and we continue doing that. So for every iteration, we scale it down. We have, if our solid cube is 27 blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9 on each set, on one face, and we have 3 slices. So our solid cube is 27 blocks. And we take away blocks, and we take away the center of each block, so 1 block per side. So we take away 6 blocks on the side, and we take 1 block in the middle. This gives us a total of 20 blocks remaining. So this means to build our next iteration, our n is equal to 20. And our scale factor, again, if this is unit length 1, our scale factor would be 3 because it takes 3 of the pieces to build that up. So our scale is 3. So our dimension is natural log of 20 divided by natural log of 3, which gives us approximately 2.73. So this shape started as a cube, which is a 3-dimensional shape, and by removing pieces of it, we're down to something that's slightly less than a 3-dimensional shape. And that's kind of cool and a little odd. So in the next video, we'll talk about a couple of other fractal shapes and their dimensions. As always, if you have questions, feel free to ask.